your videos now, your cameras now. Okay. So we have 2 talks in this first session, and I'm delighted to introduce our first speaker, Osamu Iyama from the University of Tokyo, who will talk about singularity categories and cluster categories. Thank you, Osamu.
Okay, thank you very much for introduction. And yeah, I would like to thank the organizer for organizing such a nice meeting in this difficult time. And yeah, also giving me an opportunity to give a talk here. Yeah. So today, what I will talk is about singularity categories and cluster categories. Yeah. I'm sorry, I changed my title a little bit. My original title in website is cluster tilting, but yes, actually cluster category is a more suitable title in this talk. Yeah, so yes, so I will talk about it. And everything in my talk, in this talk, is a part of joint work with Norihiro Hanihara. Yeah. So let me start to explain motivation. Okay. So yes, so my talk is motivated by studying Cohen-Macaulay representation, so-called Cohen-Macaulay representation. And yeah, actually the setting of Cohen-Macaulay representation is yes, rather wide, yes. But today I will concentrate on the following very special setting to simplify the results or statements or assumptions. So today, when I write by R, then this means R is a commutative ring. And the important point is it is a Gorenstein ring. Yeah. So this means the injective dimension of R over itself is finite. Or equivalently, the injective dimension of R over itself is equal to the Krull dimension of R. And I denote by D the Krull dimension, Krull dimension of the ring. Yes. And yes, of course, yeah, by some technical reason, I assume it is complete and local. Yeah. Now, the category Cohen-Macaulay representation theory is studied is the Frobenius category of maximal Cohen-Macaulay modules. And I denote it just by simply CMR. So CM is just abbreviation of Cohen-Macaulay, which is quite long as the name of 2 persons. And yes, Cohen-Macaulay modules have some different way to define it, but the standard definition or classical definition is that the homological invariant, so-called the depth of X, it is equal to the D, Krull dimension of D. So module X satisfying this equality is called Cohen-Macaulay, or more precisely speaking, maximal Cohen-Macaulay. And probably in non-commutative setting, yes, there's also many study about non-commutative Gorenstein ring. It is often called as Iwanaga Gorenstein ring. Iwanaga, yes. Anyway, yeah. And for Iwanaga Gorenstein ring, Cohen-Macaulay modules is usually introduced by this condition. So the condition is there is no positive extension from X to the ring R. And actually in this commutative setting, these 2 conditions are equivalent. Yeah. And this category forms the Frobenius category, and there are many studies on this category. And let me explain just 2 of the most famous results due to Auslander given in 1976. And to explain this, I assume R has an isolated singularity. Yeah, so this just means that the localization of R at the prime ideal P, which is not maximal, then RP is regular. So this has a finite global dimension. Yeah. So this is the definition of R having an at worst isolated singularity. And under this assumption, what Auslander proved is that this category, Frobenius category of Cohen-Macaulay modules, has Auslander Leiden sequence. So AR is Auslander Leiden, as everyone here I think knows. Yes. And yeah, and the existence of Auslander Leiden sequence is an application of Auslander Leiden duality in the stable category. Here I denote by CM bar R the stable category of CMR. So each Frobenius category, one can always define the stable category just by factoring out the ideal consisting of all morphisms, factoring through projective modules. Yes. Then we get a triangulated category. And yeah, this is so this is a triangulated category if R is Gorenstein. But if we additionally assume R has an isolated singularity, then the stable category has a very nice self-functor given by the suspension shift by D minus 1. So in other words, this this stable category is D minus 1 Calabi-Yau. And yes, of course, Auslander, the paper, there is no word, neither Calabi-Yau nor triangulated category, but he gave functorial isomorphism, which means, yeah, this category has a D minus 1 Calabi-Yau property. Yeah, okay. So anyway, these two results are very well known. And also another very well known results on this Frobenius stable category is that this stable category is equivalent to so-called singularity category, and it is defined as the Verdier quotient of bounded derived category of finitely generated R modules, modulo the 6 subcategory of all perfect complexes. Yeah. So this name is introduced by Orloff, but this equivalence was known from already in last century by Bookbites in his unpublished lecture note. Okay. So now, yes, so this, yes, to understand the Cohen-Macaulay representation is the one of the most strongest motivation of my talk. Now, yes, as almost everyone knows in this conference, and there is another class of Calabi-Yau triangulated category studied recently by really many people, and it is called so-called cluster category. Yeah, and it is in the hereditary setting. Cluster category was introduced by Buam, 5 author, famous paper by Buam, Marsh, Reineck, Leiten, Todorov. Then it was generalized to non-hereditary algebra by Amio for 2 Calabi-Yau case and Guo for higher Calabi-Yau case. Both are based on the work of Bernard Keller. Yes. And so now, yes, so we have 2 different types of Calabi-Yau triangulated category. One is singularity category of some Gorenstein ring, and the other is cluster category. Yeah, many recently studied very well from viewpoint of cluster tilting theory and categorification of Fomin-Zerbinsky cluster algebra. Yeah, so both are, in this sense, both are quite well studied class of triangulated category. Then, yes, for representation theorists, most natural question is to understand the connection between these 2 different kinds of Calabi-Yau triangulated category, singularity category and cluster category. And somehow, such a prototype of such a connection was already found in last century by Auslander and Leiten. And it is for simple singularity of even dimension. Or dimension 2. Bicameral periodicity, just choice of dimension does not matter. Anyway, and simple singularity is parameterized by Dinkin quiver of type ADE. Yes, and now I denote by Q the corresponding Dynkin quiver. Yes. Then there is a triangle equivalence between the stable category or singularity category of R and one cluster category of path algebra of Dynkin quiver Q. Yeah. For example, here just one example. This is for type AN. So type AN case, simple singularity is given by this polynomial. Yes, so this is the quotient of polynomial ring of 3 variables by this polynomial, and by classical by work of Auslander-Leiten in last century, the Auslander-Leiten quiver of this category is already well understood. It is just the double of Dynkin quiver Q. And double of Dynkin quiver Q is also Auslander-Leiten quiver of one cluster category of KQ. Yeah, because it is by definition the orbit category of derived category of KQ modulo Auslander-Leiten translation. Yeah, this is by definition. Yes, so it was such an Auslander-Leiten quiver. Yes, so such an equivalence was already somehow known from last century. Yeah. So then, yes, of course, yes. So this is a toy example, and we wanted to understand, more, other kinds of, equivalence between other classes of singularity categories and cluster category. So now I can state the aim of this talk. So aim of my talk is to explain certain general strategy to construct equivalence between singularity category and cluster category. So explain general strategy. This is my first aim. And the second aim is apply this general strategy to give new equivalences between singularity category and cluster category. Yeah. So this is the aim of my talk. Okay. So first, I will explain our general strategy or general result. First, I will explain general result. Then I will give some new examples of equivalence. Then I explain how to prove this our general result. So my talk, in the remaining part of my talk consists of these 3 parts. So, okay, yeah. Now let me so explain our general strategy, and somehow, yes, in any sense, our strategy is based on tilting theory. Yes. So now I just explain well-known result in tilting theory. So now let T be an algebraic triangulated category, and let A be certain finite dimensional algebra or possibly arbitrary ring. Then one of the consequences of tilting theory is that, yes, so to construct a triangle equivalence of this form, namely equivalence between T, algebraic triangulated category, and perfect derived category of A, we only have to find out a certain tilting object T in this triangulated category such that the endomorphism ring is isomorphic to A. Yeah, there is some stupid type. This must be A. Yeah. So if we find out such a tilting object, then we can get such a triangle equivalence. Okay. So somehow tilting theory is very powerful. Just find out one object, then one can immediately conclude that the full triangulated category is equivalent to the perfect derived category. So this is a so strong result. Yeah, this is essentially due to Jeremy Ricard and Bernard Keller. And now, yes, so what we wanted to do is something similar for cluster category. So instead of perfect derived category, we wanted to prove or give an equivalence with the cluster category of A. Yes. But yes, actually cluster tilting theory is not as well strong in some sense as tilting theory. We have sheer difficulty explained as follows. Namely, so yes, in contrary to tilting theory, So to construct a triangle equivalence between T and D cluster category, it does not suffice to find out certain D cluster tilting object from T. Yeah. Just finding out the cluster of, of course, cluster tilting object plays some certain role like tilting object in cluster category, but just finding out cluster tilting object does not imply such a triangle equivalence. Yeah. Yes, yeah, there are many reasons. For example, endomorphism algebra of A in this cluster category is not A anymore. It is a higher preprojective algebra of A. Yeah, this is one obvious reason why it does not work. Yeah, anyway, yeah. Now let me explain how to, our method, how to overcome such a difficulty. Yes. So basically, yes, we use the following two general notions. Well, so yes, so by construction of cluster category for non-hereditary setting by Amio, Guo, and Keller, the cluster category have canonical DG enhancement. Yeah, by their construction. And moreover, one of important point is that this canonical DG enhancement has additional Z grading. Yeah. So of course, DG category is Z graded category, but yeah. So this enhancement has another Z grading. Yeah. This is one of the point. And another point is that yes, we can also consider also for singularity category side. We consider Z-graded version of singularity category. Yes. Then we can apply tilting theory in many examples. Yes, many concrete settings. Yeah. So just somehow understand, unify these two things nicely by using DG machinery like quasi-equivalence. We can construct the such kind of triangle equivalence. So this is a very, very rough explanation of what we will do. Okay, so now let me explain our main theorem in general strategy. Yes. So yes, as I said before, I simplify Gorenstein ring side. Yeah. So yes, so very, very special class of Gorenstein ring I will discuss in this talk, but actually many things still works in much more general setting. Yeah, but I omit it but to save time. So now let R be a Z-graded ring and assume it has only non-negative parts. Yes. And moreover, as before, this ring R is Gorenstein. And we assume, as before, it has an isolated singularity. Yeah. So we have Auslander-Leiten duality. And as before, I denote by D the Krull dimension of R. And by for simplicity, I assume that the degree 0 part of R is a field, and I denote it by K. Yes. And moreover, for graded Gorenstein ring, yes, there is one important homological invariant, so-called A invariant. And it is defined by this isomorphism. Yeah. So yes, for arbitrary Gorenstein ring, so this extension from a simple module to the ring is again simple. And if we regard this extension group and K as graded module, then there is some some difference of degree. And the difference is the definition of A invariant. Yes. And so this invariant is one important notion. Yeah. And in this main theorem, let A be arbitrary finite dimensional algebra. Yes. Okay. So G-graded Gorenstein ring and certain finite dimensional K algebra is given. Now we assume that the G-graded singularity category of R is equivalent to the perfect derived category of A. Yeah. So G-graded singularity category is just a G-graded version of ordinal singularity category. So just consider the Bellier quotient of bounded derived category of G-graded finitely generated R modules modulo G-graded perfect complexes. Yeah, so this is the definition. And assume this and this are equivalent. As I mentioned before, this assumption is equivalent to that the singularity category has a tilting object whose endomorphism algebra is isomorphic to A. Yeah. So this is an assumption. So now, under this assumption, what one can prove is that so instead of G-graded singularity category, now we consider G over AG graded singularity category. Yeah. So this is, yes. So every Z graded ring can be regarded as Z over AZ graded ring. It's a kind of forgetful functor. Yeah, ignore the grading at modulo AZ. Yes. And and we can define singularity category completely same way. Just replace Z by Z over AZ. Yes. Then this graded singularity category is equivalent to the D-1 cluster category of A. Yeah. So yes. So for ungraded, so yeah. So this is a finite group. So this is very close to the usual singularity category. Yeah. There's some difference by this finite group, but it is much closer to, comparing to G-graded singularity category, this is much closer to original singularity category, and it is equivalent to the cluster category of A. And moreover, yes, actually one can also get similar equivalence for ungraded singularity category. Yeah. But yes, actually it is equivalent to not precisely the cluster category, but it's certain covering, Z over AZ covering of this cluster category. Oh, sorry, Z over AZ quotient of this category. Yeah, so we have a natural functor from above category to category in 1 to categories in 2. Yes, and basically this functor is Z over AZ covering. Yeah. Anyway, and this category is also, as in the case of cluster category, this is defined as the triangulated R of perfect derived category of A modulo certain auto equivalence. And this auto equivalence is S root of the composition of nu and minus D. Yeah. So usual cluster category is triangulated R of perfect derived category modulo composition of nu and minus D. Yes. So it is definition, or more or less definition of cluster category, and this is analog weight. Okay. So this is our main result. Okay. So now let me explain. I noticed one comment in chat. Did I say something wrong? I thought I wrote precisely the same, isn't it? Oh, yeah. It depends on setting of R. Yes, if I say yes, complete, then taking completion will be good. Yes, but actually in my talk, both graded and complete appear, and in the rest of my talk, mostly I will talk about a graded ring. Yeah. So anyway, it's something. Yeah, some small point. Okay. So now let me explain some application. So I will explain, or I will apply this main theorem to certain known setting. Yeah. Actually, there are many examples of Gorenstein ring such that the G-graded singularity category has a tilting object. Yeah, there are many such graded Gorenstein rings are known. Yeah, and I will not try to list up all known such equivalence. I just explain only 3 or 4 examples in this talk. And let me start with the simplest case. So the simplest setting is dimension 0, crude dimension 0. So R is just finite dimensional algebra over field. So R is G-graded Artinian Gorenstein ring, and as before, I assume degree 0 part is a field of K. Then R is finite dimensional K algebra, and in this case, the A invariant is nothing but the degree of circle of R. So largest, in other words, largest non-zero degree of R. It is the A invariant. And in a paper by Yamaura in 2013, he proves that, actually he deal with non-commutative self-injective algebra in his paper. So this is just a special case. And actually he proves that, yes, so this category has a tilting object, and it is explicitly given by this formula. So consider degree shift of R. Move it I step to the above. So this I it means degree shift factor, and then truncate. We cut out all negative degree to get module which is non-negatively graded, and actually this gives us a tilting object. In particular, the G-graded singularity category is equivalent to the perfect derived category of A, and actually one can easily describe the endomorphism algebra of A in this matrix form. But it is not so important in here. And yes, actually by applying our main theorem.
Sorry, is our commutative here or not?
Actually, yes, I assume commutative here, but actually, this is a tilting, and this works for arbitrary non-commutative self-injective algebra. So this works also for non-commutative setting.
I mean, if it's commutative, it's just exterior algebra of finite dimensional vector space, right?
Well, exterior algebra,
maybe not,
this is
maybe
very
not
general Gorenstein ring. Artinian Gorenstein ring. Of course, exterior algebra is one of such an example, and also polynomial ring modulo power of variables. This is also Artinian Gorenstein ring. So there are many examples of such R. Okay. And yes, by applying our main theorem, we can get such kind of triangle equivalence. So because dimension of this ring is 0, so we get equivalence with -1 cluster category. So they are -1 Calabi-Yau. And I should remark that Yamaura also in his paper gives such kind of triangle equivalence. Already. I think, this one, I think. Okay, so this is dimension 1 case. So next is, well, dimension 1. Yes, so now we are in the setting of Krul dimension 1. And yes, so again, we consider G-graded Gorenstein ring of dimension 1. And here, I assume it is reduced. So this assumption corresponds to our previous assumption of having an isolated singularity. Yes, and as before, I assume the degree 0 part is field, and I denote by A the A invariant of R. Yes. Then in relatively recent work with Bookbites, Ragnar Bookbites and Yamaura again, we prove that the G-graded singularity category contains a tilting object. Yes. And this tilting object also is given by almost same formula as in the case of dimension 0. But the difference is that, yes, again, we consider degree shift of R by I to move up, then cut out, remove negative degrees. Yes, and the difference is that, yes, we need to, so this number is not given by A. We can also describe this n explicitly, but it is enough if n is sufficiently large. Taking n sufficiently large does not change the additive closure of T, so we can choose arbitrary large n. Then, yeah, by tilting theory, the G-graded singularity category is equivalent to the perfect derived category of endomorphism ring of T. Yeah, actually, one can also describe this endomorphism ring as in the case of Archinian setting, but I omit it. And what is important for us is that by applying the main theorem, we get to, yeah, triangle equivalence of, yeah, similar type. Yeah. Yeah, in this setting, Krull dimension is 1. So what we get is 0 cluster category. Yeah, so they are 0 Calabrian. Okay, yeah. So now, so yes, so this is an example from dimension 0 and 1. And yes, there are also many study of hypersurface singularity in dimension 2, such that the G-graded singularity category has a tilting object. Yeah, for example, Geigel or wrenching Kushin-Meltzer wrenching or Kajiura Saito Takahashi, or yeah, many people give such an equivalence. And yeah, but yes, today I want to talk about the quotient singularity instead. And yeah, big one reason is yes, Krull dimension can be arbitrarily large here. So now I consider arbitrary field K and consider a finite subgroup G of special linear group over K. And I assume minor assumption about the yeah, order of G, which is not divisible by the characteristic of K. So this is some assumption. And now I denote by S the polynomial ring of D variables, and I consider the invariant subring of natural G action on S, and I denote it by R. Yes, and this R is actually Gorenstein ring in Krull dimension D, and actually the A invariant of this ring R is given by minus D. Yeah, it is equal to the A invariant of S, which is minus D. Oh, yes, yeah, I should explain Z grading before. So Z grading is given in a way that every variable have degree 1. Okay, then invariant is minus D. Okay, and now, yes, in a work, joint work with Ryo Takahashi, we prove that the singular, okay, yes, yes, the singularity, G-graded singularity category of R has a tilting object, yes, and yes, I forget to assume one assumption. So assume R has an isolated singularity. Yeah, this is not automatic for arbitrary subgroup G. So assume R has an isolated singularity. Yeah, and this is also equivalent to that. The action of G on the D-dimensional vector space KD, this action is free except at the origin. Yeah. Anyway, in this assumption, under this assumption, we can construct the tilting object by using the syzygy of K as an S module. Yeah. So consider the ith syzygy of K as an S module and regard it as an R module. And this is not Cohen-Macaulay, but yes, we can take maximal Cohen-Macaulay direct sum and then take direct sum of it, we get a tilting object. Yeah. In particular, as by tilting theory, we get such a triangle equivalence between G-graded singularity category and the perfect derived category over the endomorphism ring. And by applying our main theorem, yes, we again get equivalence between singularity category or G over DG graded version of it and cluster category and certain covering of it. Yeah. Okay. Certain quotient of it. Yeah, anyway. So now, so this is another example. Yeah, maybe, yes, I should have prepared some more concrete example by quiver with relation given by Mackay quiver, but yes, I did not have time to do it. So now, yes, let me explain some more other example. Yeah, actually, as I said before, main theorem I explained is somehow is the simplest setting, and actually it can be generalized to also for suitable non-commutative rings like symmetric order over Gorenstein ring, and also, yeah, in the theorem I assume R is Z graded, but also, yeah, there are some G graded version. Yeah, we can replace the abelian group, giving a grading on R by some more general ring. Yeah, and let me give actually, yeah, a commutative Gorenstein ring, which is not Z graded, but graded by some other abelian group. Yeah, and yes, one very famous example is so-called weighted projective line. And also its generalization to higher dimension, so-called Geigel-Lensing complete intersection. And it is defined as follows. So now consider a polynomial ring of D variables. So this is the first input. Then we need to give some linear forms, L1 to Ln. N can be arbitrary, yeah, possibly 0, or yeah, can be very large. And what we need to assume is that these linear forms are as linear independent as possible. Yeah. So yeah, of course, if we choose N is bigger than D, then they cannot be linear independent, but every choice of at most D linear forms are linearly independent. Yeah, so this is an assumption, and moreover, we need to fix certain positive integer p1 to pn for each linear form. Yes. Then we can define a complete intersection ring, Gorenstein ring, by consider a polynomial ring over S by adding n new variables and factor out a regular sequence consisting of xi to the pi minus li. Yeah. So this gives us a regular sequence, and yeah, this R is a Gorenstein ring. Yeah. And yes, actually the case D equal to is a very famous example of weighted projective line. Yes. And this Gorenstein ring R is graded by certain abelian group of rank 1, which is usually denoted by L, and it is defined as a quotient of free abelian group with basis xi vector and c vector modulo the subgroup generated by this relation. Yeah. And actually, yeah, this relation is very natural, or this grading is very canonical. What we want to do is to make every variable ti and xj homogeneous. And yes, actually the degree of xi new variables is given by vector x, and the degree of all the variables tj is given by c, additional element c. Yeah. Then this relation, or this element is homogeneous, must be homogeneous. Therefore, we take a quotient by such a subgroup. Yeah. So degree of this is p times xi, and the degree of li is c. So they must be the same. Yeah. Okay, so now anyway, so we get Gorenstein ring graded by this abelian group. Yeah, this abelian group have rank 1 and in general having a torsion element. Okay, and yes, so about the tilting theory of this Gorenstein ring, yeah, it is known that yes, there is a triangle equivalence of this form for certain A. It is a finite dimensional algebra explicitly described by quiver with relation, or yeah, also, yeah, we can construct categorically by using a certain R modules anyway. Yeah, and this such an equivalence is given by my paper with Hershendo, Minamoto, and Opperman, and the case weighted projective line is given by Kushin, Meltzer, Lensing, and also hypersurface case, namely n equal d plus 1. In this case, it is given by Futaki and Ueda. Yeah. Anyway, So we have such a triangle equivalence, and this algebra have very concrete description for hypersurface case. Yeah, actually, n equal d plus 1 case. What's happened? Something strange happened. How to ignore this? Okay. Yeah. Okay. So n equal d plus 1 case. This algebra A is a tensor product of path algebra of linear oriented type A quiver. Yeah. So yes. So A have very explicit description. And now by using L graded version of our main theorem, one can prove, we can deduce that the singularity category of R, L over omega graded singularity category of R, where omega is an A invariant of our ring R. Yeah, there is also L graded version of A invariant. Yeah, and this graded singularity. So this is a finite group. Yeah, so this is very close to ungraded singularity category, and it is equivalent to the D-1 cluster category of A. Yeah. So as a conclusion of our theorem, we get such a triangle equivalence. Yeah. So now, yes. So now I give last example in my talk. And yes, actually, it is so-called Grassmannian cluster category. Studied by many people recently in the connection with categorification of homogeneous coordinate ring of Grassmannian. And Grassmannian cluster category is defined also as a singularity category of certain Gorenstein ring. And the ring is one-dimensional and given in this very simple way. Yeah, it is a polynomial ring of two variables modulo this one relation, xl minus y n minus l. And actually this ring does not have nice z grading, but it is graded by z over nz. Yeah, degree of x is 1 and the degree of y is -1. Then this element is homogeneous, so R has g over ng grade. Yes, and actually by applying L graded and moreover certain hypersurface version of our main theorem, one can prove that this Grassmannian cluster category is actually equivalent to the two cluster category of tensor product of type A, two type A quiver. Yeah, a type A quiver of A L-1 and A N-L-1. Yeah. Actually, this, as far as I know, this explicit equivalence was not written anywhere. Yeah. Of course, taking certain ideal quotient by general theory, we get equivalence. But yes, we can get triangle equivalence in this level. Yeah. Actually, let me a bit explain how to get to this. Yeah. Actually, this equivalence is in some sense deduced from our previous equivalence for Geigel-Lenzing complete intersection. Yeah. The reason is very simple, because this ring, hypersurface ring R, is a special class of Geigel-Lenzing complete intersection. Yeah, actually by adding one additional variable T1, yes, and then factor out these two elements, yes, then this ring R is coincide with this ring. Yeah, just to kill the variable T. Yes. Then, yes, so this is actually, by definition, it is a special case of Geigel-Lenzing complete intersection by choosing D equal 1, N equal 2, and P1, P2, and L1, L2 in this way. Yeah, anyway. And then, yes, this ring R is Z over NZ graded, but actually this Z over NZ grading is actually a simplification of L grading for Geigel-Lenzing complete intersection. Actually, there is a surjective map from L to Z over NZ. Yes, just factoring out L by one element, Lx1 minus N minus Lx2. Then, we get canonical isomorphism between this quotient and this quotient. Yeah. So in this sense, we can deduce this equivalence from not directly from this, but yes, hypersurface modification of this equivalence. Yeah. I'm sorry, I don't have explained this hypersurface version in this talk here. Yeah, in the last 10 minutes, I think I wanted to explain, how to prove our main theorem. Yeah, so I think I have 10 minutes, right, or 15 minutes. I forget the time. Yes, the time.
So you have around 5 or 6 minutes. Is that okay?
Oh, 5 or 6 minutes. Okay, thank you very much. Yes, that's enough. Quite enough. I think. Yes, let me try. Yeah. So now this is a proof part of our main result, and proof is everything is depends on the machinery of DG category. Yeah. So yes, so first of all, let me remind you the definition or canonical enhancement of cluster category, or slightly more general orbit category, triangulated orbit category. Yeah. So now I denote by A the DG category over K, and as usual, I denote by A is the enveloping category. And let V be a certain cofibrant DG module over the enveloping algebra category. Then we can define DG orbit category A over V in by this formula. Yeah. So as is usual, so orbit category have same objects as original category A. And morphism space is basically defined by taking direct sum of degree n part. Yes, and yes, that degree n part is given by this. Yeah. So yes, so this is A module, DGA module. So this is the tensor power of V over A n plus I times, and this is I times, and by evaluating object from right side, so they are right DG module over A, and then home complex as DGA module gives also as a chain complex. And this gives us a morphism complex of part of morphism complex of DG orbit category. Yeah. Yeah, always this definition is quite compressed, and looking at this picture gives a better hint. Well, yeah, so this is actually, so this by this definition, yeah, so every term have canonical differential, and one of the point is this DG category has canonical additional Z grading. Yeah. So everything is chain complex, so already have Z grading, but here coproduct appear, so this coproduct gives us additional Z grading. So degree 0 part is, actually colimit of such a map, and degree 1 part is colimit of such a map, and so on. Yeah. Anyway, so this is DG orbit category, and yes, actually, yes, cluster category is defined by as a special case of this construction of DG orbit category. So yeah, so we start with A, the perfect DG enhancement of perfect derived category, and take a cofibrant resolution of K dual of A, shift by -D. Then we can, so this P tensoring with P gives us a DG functor from A to itself. Yes, and therefore it gives us some module over the enveloping algebra, and applying our previous construction, we get the DG orbit category, and cluster category is by definition the perfect derived category over the DG orbit category. Yeah, so this is just a reminder of the construction. And yes, so this is just a reminder, and now let me explain our point, or important step of our main theorem, proof of our main theorem. So yes, so anyway, DG orbit category have additional Z grading. So now let me, so we consider somehow opposite construction. So start from DG category with Z graded, additional Z grading. So B have G2 grading, and one grading is closely, differential is very, differential changes first degree grading, but it does not affect the second degree. Yeah, so this is G graded DG category, and for such G graded DG category, we can define G graded derived category and G graded perfect derived category as usual, just by considering G graded DG modules. So now let me explain key proposition. So we start with G graded DG category B. Yes. And now we assume one crucial assumption. So this assumption is very important. So G graded perfect derived category is generated by just representable functor over B as a 6 subcategory. Yes. So this assumption is very strong. Yes. Why this is, yes, maybe, G graded perfect derived category is generated by degree shift of all representable functor. This is the definition. Yes. So we need a degree shift to generate G graded perfect derived category. But here we assume, yes, just a degree 0 representable functor without any degree shift generates perfect derived category. Yeah, this is a very crucial assumption. And in this setting, yes, actually this B can be recovered from its degree 0 and -1 part. So I denote by A the degree 0 part of B. It has a natural canonical DG category structure, and degree -1 part have also canonical DG module structure over the enveloping category. Yes. Therefore, we can construct DG orbit category as before. And yes, actually, what one can prove is that under this assumption, this G graded DG category and this orbit category are quasi-equivalent, which preserves Z grading. Yeah. We are considering G graded DG category, so they are not only just quasi-equivalent, but there's a quasi-equivalence preserving G grading. So this is one important point. Just degree 0 and -1 part recover every DG category. Yeah, so this is one of the point. And another ingredient is that we assume that our G graded DG category have certain Calabi-Yau structure. Or it is Calabi-Yau in this sense. So taking K dual of B, then it is isomorphic to B with certain shift, degree shift by -1 and homological shift by D as a module over enveloping algebra. Yeah, this is a kind of Calabi-Yau property. And if we assume this, then the point is B -1 part is very explicitly given by K dual of A. This is a point, and as a consequence of first statement, we get this equivalence. Yeah. So first equivalence, actually this is isomorphism in the category of DG category with quasi-equivalence is inverted. Yeah. This category appear in Keller's ICM survey article denoted as HQE. I don't know how to call this. Yeah. Anyway, in this HQE category, these DG category are isomorphic, and also ungraded version of DG, perfect DG category of B is equivalent to the perfect DG category of orbit category. Yeah. So this is a crucial point. Yes. And yes, this is one very key ingredient. So so basically this part gives us a cluster category, and this part plays a role of singularity category. Yeah, so this is, so somehow one can imagine how we can deduce our main result from this isomorphism. Yeah, so this is a very simple explanation. And yes, there is also another ingredient, certain DG enhancement of singularity category enjoy this Calabi-Yau property. Yeah, this is actually another key ingredient. We call it as an enhanced Auslander-Leiten duality. Yeah, because taking zeros cohomology of this equivalence gives recover the classical AR duality. Yeah. Anyway, we can prove AR duality in DG category level, and this is another key ingredient of proof of our main theorem. Yeah. And yes, I think I should stop my talk here. And thank you very much for listening.
Thank you, Osamu. So let's first thank Osamu for a very nice talk. We have time for a couple of quick questions.